Okay, I want you to try and solve this in your head right now. 465 plus 230. Seriously, give it a shot. Okay, so now think about exactly how your brain just arrived at 695. Chances are you didn't picture a piece of lined paper, stack the digits, add 5 plus 0, then 6 plus 3, and then 4 plus 2. No way. If you did it in your head, you probably used a much more natural approach. You might have thought, well, 400 and 200, that's 600. 60 and 30 is 90. Add the 5, 695. See, you went from left to right. You broke the numbers into chunks that actually made sense to you. You used a strategy you invented intuitively, rather than some rigid set of steps you memorized back in 3rd grade.
Welcome to this explainer. Today, we're totally rethinking math computation. We're pulling some fascinating insights from Chapter 11 of the foundational textbook, Teaching Student-Centered Mathematics, specifically pages 183 through 189. We're diving into what is honestly a massive paradigm shift in how we understand learning. We are talking about moving away from the rigid memorization of traditional formulas and instead fully embracing flexible, student-invented math strategies. Here's our roadmap for today. First, we'll rethink fluency, then trace the journey from modeling to inventing. After that, we'll look at how to cultivate an inventive environment, compare invented strategies with standard algorithms, explore the long-term benefits, and finally, look at the pedagogical case for delaying the standard algorithm.
Okay, Section 1, Rethinking Fluency, Beyond Speed and Memorization.
For a long time, the public, and frankly, a lot of us in education, have viewed mathematical fluency as just being really fast and perfectly accurate with a set of memorized steps. But our source material challenges us to completely flip that definition on its head. Looking at the Common Core State Standards and the text adding it up, procedural fluency is defined as skill in carrying out procedures flexibly, accurately, efficiently, and appropriately. Notice that very first word? Flexibly. True computational fluency isn't about blindly following a recipe. It's about looking at the numbers in front of you and choosing the absolute best, most appropriate strategy for that specific situation. It's a bird's eye view of the math, not just a heads-down rote memorization drill. Section 2, From Modeling to Inventing, the Cognitive Journey. So, how do students actually achieve that flexible, procedural fluency? Well, it happens in 3 major phases. Step 1 is where we literally all start, counting by ones. If a kid wants to add 4 and 7, they count 4 things, then they count 7 things, and then they count them all together again. Step 2 is direct modeling. This is where students use physical manipulatives, like base 10 blocks or drawings, to represent the operation. But the ultimate goal? That's step 3, invented strategies. This is a huge cognitive leap, where students stop relying on physical objects and start using mental relationships. The really absolutely crucial point here is that an invented strategy is any method other than the standard traditional algorithm that doesn't involve using physical materials or counting by ones. Instead, these strategies rely entirely on a solid grasp of place value and the properties of operations. When a student invents a strategy, they're taking numbers apart, shifting them around, and putting them back together based on a deep internalized number sense. It's a messy, but honestly beautiful phase of learning. Section 3. Cultivating an inventive environment. Creating mathematicians. If we want students to develop these brilliant, flexible strategies, we can't just stand at the front of the room and lecture at them. We literally have to transform the classroom into a laboratory for mathematicians. First off, avoid immediately identifying the right answer. Actually, scratch that. If a student says the answer is 695, don't just say correct. Turn to the rest of the class and ask, hey, do we agree with that? Why or why not? We have to expect and really encourage student-to-student debate. Discuss both right and wrong ideas in a completely non-threatening way. Mistakes? They're just data points for learning. When you promote curiosity and risk-taking, students feel safe enough to test out new mental pathways and share those emerging ideas with their peers.
Section 4. Invented versus standard. The great contrast.
So how do these student-invented strategies actually stack up against the traditional standard algorithms most of us were taught? The differences are pretty profound. For starters, invented strategies are number-oriented, while standard algorithms are digit-oriented. Let's think about adding 416 and 329. With an invented strategy, you look at the whole numbers and think, okay, 400 plus 300 is 700. You preserve the true scale of the values. But the standard algorithm? It just chops the numbers up. It tells you to line them up and only look at the digits in the hundreds column, saying 4 plus 3. It totally obscures the fact that you're actually adding hundreds, not single digits. Furthermore, invented strategies are what we call left-handed, while standard algorithms are right-handed. When students invent a method, they almost always start with the largest values on the left, just like we did with 465 plus 230 at the very beginning of this explainer. This is incredibly powerful. Why? Because it gives you an immediate, intuitive sense of the size of your final answer in just one single step. In contrast, standard algorithms force you to start on the right with the tiny ones column, hiding the actual meaningful result from you until the very end of the process.
This contrast is so stark that Constance Kamayi, a really prominent researcher cited in our source text, reached a striking conclusion. She says standard algorithms actually unteach place value. Let me say that again. They unteach it. By forcing students to think in terms of isolated, detached digits, they lose sight of what the numbers actually represent.
Section 5. Benefits of inventing. The long-term payoff.
So if standard algorithms can actually be harmful when introduced too early, what's the long-term payoff of spending the time to foster these invented strategies? It really boils down to this fundamental insight from researchers Gravemeyer and Van Galen. Students using methods they understand make many fewer errors than when they use strategies that they just memorized. I mean, it makes perfect sense, doesn't it? When a student memorizes a standard algorithm without really understanding it, their errors tend to be systematic and notoriously difficult to fix. But when they build a strategy from the ground up, based on their own logic, their errors are rare, and better yet, they can easily correct them themselves. And the practical payoffs for the classroom, they are undeniable. First, because the learning is actually sticking, teachers find that significantly less reteaching is required down the line. Inventing strategies also guarantees a really robust development of number sense, and it forms the exact basis we need for fast mental computation. In fact, these flexible methods are often way faster than writing out all the steps of a standard algorithm. And for anyone worried about state testing, get this. The evidence shows that students who've used invented strategies perform equally well or even better on standardized tests. This is largely because it drastically increases their ability to tackle complex word problems.
Section 6. Delaying the standard algorithm. A pedagogical case.
If invented strategies are this beneficial, and standard algorithms can literally unteach place value, our source text reaches a very specific and perhaps to some controversial conclusion: delay, delay, delay. Look, you're going to need to introduce the standard algorithm eventually. It's part of the curriculum, but you absolutely must delay it for a significant amount of time. We're talking months here, not weeks. The goal is to allow a student's own invented strategies to fully, completely solidify first. Once they have a deep, unbreakable number sense, well, then you can introduce the standard algorithm simply as one more tool in their diverse toolbox, rather than the undisputed boss of mathematics. It's really important to realize that this pedagogical framework, originating in teaching student-centered mathematics, isn't just some abstract theory. It's a rigorously researched approach to developmentally appropriate instruction. The authors emphasize that if you introduce the standard algorithm too early, students will immediately assume it's the right way, and they'll just stop trying to make sense of the math for themselves. You have to protect that period of invention.
And as a fascinating side note, we also need to recognize cultural differences. What we call the standard algorithm here in the US, it's not a universal language. Different countries have totally different conventions, notations, and traditional algorithms. Assuming there's only one right way to stack and solve numbers doesn't just limit mathematical thinking,
It completely ignores the rich, diverse approaches that students from different backgrounds bring into the classroom. So, what does this all mean for us? I want to leave you with this final, somewhat provocative thought. If you have the courage to delay the standard algorithm, if you step back and create a space where mistakes are just data and numbers are flexible, what mathematical brilliance will your students invent today? By shifting our focus from mindless memorization to genuine understanding, we aren't just teaching kids how to calculate, we are teaching them how to be real mathematicians. Thanks for exploring this explainer with me, and keep cultivating that curiosity.